Okay. We're going to continue decoherence and the quantum mechanical evolution to the classical. And we did quite a bit last week. Let me, I guess I need to go to the,
Hey, Bob,
yeah?
we have a new member, and I thought we might just get him to introduce himself.
Oh, okay.
Do you want to just tell us something about yourself?
Okay. My name is Adrian Byram, and I studied math and physics at the University of Toronto back when Newton was a child.
We all did, but that's right.
And then I worked on a PhD at Stanford in a thing called engineering economics systems, which was in the early 70s. But I left and started the company before I finished my PhD, actually, and worked in the IT industry and for most of my career. And then I retired about 7 years ago and went back to school and and then did a PhD in neuroscience and ethics.
Oh, good.
At the University of British Columbia.
Wow.
And then we moved here about a year ago, about 6 months ago. So, I'm very interested in solar power and sustainability, and I'm going to be taking over as the chair of the solar committee at Sustainable National.
Oh, you are? Okay.
At the beginning of the year. So
Okay, good.
if anybody has ideas about that or can help me in that in any way, I'm more than.
Do you know Barry?
Yeah, yes,
okay.
yeah, Barry. Working on. He's taking over other rural things that's sustainable. I'm taking over that from him.
Well, I'm all for you. We have solar in our unit, so I think it's great.
Mm-hmm.
Anyway, last week we talked a little bit about what we're doing about quantum theory, where finally we've reached the stage that classical physics can be a subset of quantum theory. And we talked quite a bit about the classical phase space, configuration space, momentum space, all of these different things that are important to understand. We only gave a very crude description of how decoherence works, and we're going to get that next week. But this week, we're going to talk about entanglement. And we talked a little bit about how Bohr described quantum mechanics, and he create a distinction between quantum and classical without defining what it meant. And this was Bell's shifty split that he talked about. We're going to discuss much more about how that is not accurate. And we're going to get to contextuality, hopefully, at the end of the day today, which will understand more of how that doesn't occur. So could somebody quickly describe linear vector spaces and configuration space, which we talked about last week?
I could try.
Go ahead.
Well, configuration space, let's think of two. If I'm going to be able to draw anything on the board here, I'm going to have to restrict myself to one dimension. Okay, so think of red bead and a blue bead sliding on a wire. Okay. Now you can represent the positions of these two beads either in several ways. One is to think of them as two separate beads and describe their position by two numbers. The distance, say, of the red bead from the arbitrary origin, put it on the left. And another number which describes the position of the blue bead. So let's call this number XR for X of the red bead, and this number here, the distance of the blue bead from the origin, as X of B. Okay. So here's one way of representing this situation. Two beads, one number for each bead. Now there's another way of doing that by just 1 point instead of 2 points, and that is to construct a two-dimensional diagram, one dimension for each particle. So we might have vertical axis describing, representing the position of the red particle, horizontal axis representing the blue particle. So the red particle is a distance XR from the origin. So this is our origin here. We'll go on the distance of XR. So
Great.
And the blue bead is a distance XB from the origin, so we'll represent that along the blue axis. So this distance here is XB. And then we can describe these two numbers by putting a point, 1 point here, whose XB component represents the distance of the blue bead from the origin, and whose XR component represents the red bead's distance from the origin. So here we have 1 point representing both the distances of both beads from the origin. Okay. This is the lowest, this is the highest dimension I can go, and still go up and down the board. If we think of each of those particles as being in free space, in ordinary Euclidean space, then we would need 3 numbers to describe the position of each particle. Its X, Y, and Z components, and we can represent both particles by 1 point if we go to a 6-dimensional space. The first 3 dimensions may represent the position of the red particle, and the 6th dimension would represent the position of the blue particle. So clearly this is not a real space, this is a mathematical space. But it's a very convenient way of visualizing the configuration space. By that, I mean the space representing the position, not the momentum, just the position of all the particles. So if we have n particles, we need a 3n-dimensional space. But the concept is no different than what I've done here. You just have to think mathematically in terms of many dimensions, even if you can't draw or visualize.
Thank you, Steve.
Okay.
The only thing I would comment is the wave function in quantum mechanics doesn't live in space.
You're in,
It
Steve.
lives in configuration space.
Hey, Steve, could you switch your camera so it points at the board?
Yeah.
I,
What's that?
I just wanted, just instead of looking this way, no. Oh, well, you could,
Just leave it. It's fine. Thanks.
okay.
All right. Okay. We've talked about spaces and especially configuration space, and we're going to talk about entanglement, particular and contextuality, hopefully today. And then next week we'll do closed systems, open systems, quantum mechanical systems, and the quantum mechanics of open systems, which leads to decoherence, line selection, and pointer states. Anyway, once you have pointer states, you have classical physics in quantum mechanics. So let's move on to it. Quantum entanglement gives what many people are the heart of what is weird about quantum mechanics. And it's got a very glamorous mystery attached to the concept of quantum entanglement. Yet, in the end, these are just simple, down-to-earth meanings with concrete implications, and hopefully I'll be able to explain it as clearly as I know how. So, entanglement is often regarded as a uniquely quantum mechanical phenomenon, but it's not. In fact, it is actually enlightening to consider a non-quantum or classical version of entanglement first. And this lets us begin to pry the subtlety of the entanglement itself from the general oddity of quantum theory. Suppose we have a couple of different systems. We'll call them classical systems or seons, C to mean classical. And if you want to think about it, you can think about it as cakes. So here's one system. Our first system has a round yellow cake, and the second has a chocolate square cake. And our second system has a square cake that has a red icing and a round cake which has a green icing. I managed to grab it from MacArthur Park and get it into this system. Anyway, our seons or cakes come in two shapes, square or circular. And we can identify them as their possible states. We're going to throw out the weight and the taste and the depth. We're just going to deal with the shapes here. So from our two systems, there's four possible joint states if we measured them. We could find one to be square, square. We could one to be square, circle. One could be square, circle. I mean, circle, square. And lastly, circle, circle. And this shows the independence of the two sets of systems. So you could have, as I said, a system that was circle, circle, 1 and 2, and there could be a square circle, 1 and 2, a circle square, 1 and 2, and a square square, 1 and 2.
So Bob, you're picking one from each system.
I'm picking one from each system.
Okay.
And choosing them independently. And since they're independent, that means the probability of each one is 25%. So it's the fact that it's independent says that the knowledge of the state of one does not give us any useful information about the state of the other. And that's what our first table had in this property. So if the cake is square, we're still in the dark about what the second one is that we choose, and it could be either a square or a circle. On the other hand, we could say our two ceons are classically entangled when the information about one improves our knowledge about the other. So the next table I'm going to show demonstrates extreme entanglement, classical entanglement. And in this case, whenever the cake is circular, we know the second is also circular, or if it is square, we know it's also a square. So in this case, the two cases where it's either a square and a circle has 0 probability, or a circle and a square also has 0 probability. But as I said, knowing one about it being a circle knows for sure that the second one is also a circle. And similarly, if it's a square, we know it's also, the second one is also a square. So but we don't know which of those two systems are, so the probabilities for those two systems are 50% each. Are people understanding what this is all about?
You know, I really don't understand the diagram on the board. Would you go over that again?
Okay, we have set up two systems, a circle and a square and a circle. In this case, we have set up the choices to be only either a circle circle or a square square, but we don't know which. So there's 50% chance that it's circle circle, and it's 50% chance that it's square square. However, if you know that one of them is a circle, you know with 100% correlation that it's also a circle. And if you know that it's a square, then you've got a 100% correlation that it's also a square. Did that make it any better?
No, the thing I'm missing is your axis. Your axis is vertical is system 2 and the horizontal is system 1. Now, what does that have to do with what's inside the...
Whenever you choose a square in system 2, you must choose a square in system 1. And whenever you choose a circle in system 2, you must choose a circle in system 1. That's the rule.
Okay, so that's just a rule.
That's the way the system works. That's what a entangled system works. If you know something about its square in system 2, you know automatically with 100% truth that it will be also a square.
Okay.
And similarly, if the system is a circle, the other system is 100% sure to be a circle. That's the way we've set up the rules. And that's what entanglement means, that they're 100% correlated. Now, you don't know which of these two it is, That's why it's 50% chance of this and 50% chance of this. But their correlations are 100%. If it's circle, it's circle. If it's square, it's square.
Okay, and the other possibility, if it's circle, the diagonal, other diagonals can't exist
That's right. That's why they have 0%,
according to the rules.
according to the rules.
Okay, I'm kind of there. Is everybody else?
Yeah.
Was that a yes or a no? I can't tell.
Yes.
This is just the setup.
Yeah, well, that's a setup. But if I don't understand the setup, I won't understand the rest of it. So.
The quantum version of entanglement is essentially the same phenomenon. That is the lack of independence. Cakes don't count as quantum systems, of course, but quantum entanglement systems arise naturally. For example, in the aftermath of a particle collision. By the way, collision is really a bad term because it tends to think of like two billiard balls hitting each other. But in point of fact, the way quantum mechanics work is all you know is two electrons, for example, get in a local region of each other, and two electrons come out, but we don't know if what they do when they're in the middle of the two of them, except that they become entangled. That is the nature of a collision, quote unquote. And collision is a very bad word because it makes you think of billiard balls, and these are not billiard balls, they're quantum systems. Is that clear about people?
Yeah.
Entanglement was discovered by Albert Einstein in his famous 1935 EPR article, Einstein, Podolsky, and Rosen, for those who don't know EPR. And Bohr was so befuddled that he wrote a long article to supposedly rebuttal Einstein's argument. But as Lenny Susskind has said, both Bohr and Einstein were subtle men. Einstein tried very hard to show quantum mechanics was inconsistent. Bohr, however, always was able to counter his arguments. But in his final attack, Einstein pointed out something so deep, so counterintuitive, so troubling, and yet so exciting that at the beginning of the 21st century, now, it has returned to fascinate theoretical physicists. And for several years, Einstein's 35 paper was the most referred to article, most cited article for several years. And in this long, befuddled article, Bohr's only answer to Einstein's great discovery, the discovery of entanglement, was to ignore it. The article is just complete nonsense, and there's the only information that deals with it are in two footnotes, one footnote and then a footnote to the footnote. Mm-hmm. And they don't say anything in them. It's a complete nonsense. The fact that somebody actually allowed it to be published is just nonsense.
Okay, so, I'm sorry, go ahead.
Okay, so the quantum version of entanglement is essentially the same phenomenon, the lack of independence.
Bob?
Yeah,
question?
I think I went the wrong way. Yeah.
I want to ask
Miguel
you
has a
something,
question.
Bob. You've spent several minutes talking about this article that Einstein that was so incredible and then it was the most cited and then now it's nonsense. Can you give us a hint as to what the article said?
The Einstein.
Oh, this is the famous EPR.
Well, the response was nonsense.
Yes.
Okay, well, still, I still don't know what the article said. I mean, obviously.
The article basically said that if you took a look at position and momentum, those two are non-commuting observables. That is, non-commuting operators. And that means that you can't measure both of them at the same time. However, Einstein showed that if you had entangled particles, then you would know either the other position of another particle if you knew one of them. This is the fact that they're 100% correlated, or the momentum could be 100% correlated, either one. And since they would be 100% either one and you didn't know which, the assumption was you had to know a priori that both of those characteristics were true. And that is certainly true in classical physics, but it is not true in quantum mechanics. Unfortunately, Einstein, although he discovered entanglement and it was very important, his result, his answer at the end turned out not to be true. That was not shown by Bohr, it was shown by Bell, Specken, and several others, which we'll get to in contextuality.
So Bob, just going on EPR a little bit, he measured the position of one particle, and since they were entangled, he could deduce the position of the other particle, and then he measured the momentum of the second particle.
No, he didn't measure him. He said you have two possible systems that you could measure. One, you could measure two positions with 100% correlation, or you could have two momentums with 100% correlation. And the assumption he made was that these properties had to be true simultaneously. If you could know one or the other, and you didn't know which one you measured, you didn't have to know which way you were going to measure it. You just know that either the positions were true and the momentums were true.
Bob, can I make a couple of remarks here?
Sure.
The idea is the following. You can think of it this way. You create two particles, two entangled particles. One zips off to the left, the other zips off to the right. Now you can choose to measure, say, the position or the momentum of the particle on the left. Let's say you choose to measure the position. You measure it, then you know the position of the particle on the right because of the entanglement. On the other hand, you could choose to measure the momentum. And measuring the momentum of the blue particle then tells you what the momentum of the red particle is. So Einstein said, because you're not disturbing the red particle by doing things to the blue particle, the fact that you could choose to measure the position or the momentum of the blue particle without disturbing anything having to do with the red particle means that both of those quantities must exist in the red particle. You could choose to measure either one without disturbing it. That's the thing. His fundamental assumption was that you don't disturb the red particle by doing anything to the blue particle.
Well, you have to know something about the the system of the two particles, right? I mean, you're saying one's going to the right, one's going there. You have to have some description of that.
Exactly. Yeah, sure.
Yeah.
The
So they
simple,
have to be entangled. And because they're entangled, you know 100% what the other one is going to do.
I understand that.
That's the definition of entanglement.
What is the description to begin with that you know what that system is?
well,
In other words, is there some equation that says this is the way two particles interact, and so if you know the position of one, you're going to know the
I
other?
guess the simplest example that people have actually used in experiments was you take an excited atom that when it de-excites, it emits two photons. And the two photons are correlated in the sense that the polarization of one and the polarization of the other ones add up to, say, zero polarization by the nature of the de-excitation of the atom. Okay, so you know what the polarization state. If you know the polarization state of one atom, then you know the polarization state of a photon, I should say. Then you know the polarization state of the second one. So that's an example of where the details of the experiment are known. It's not hypothetical.
Okay, got it.
Yeah. And the idea again is the critical argument is locality, that these particles can separate great distances. You know, you can let them go as far as you want, and you do something, make a measurement on one particle. And Einstein was claiming that that can't disturb anything. It can't do anything to the second particle. And since you have the choice of measuring two non-commutative properties, choose one or choose the other, you're not disturbing the second particle. And each time you measure a property of the first particle, you know what the property is of the second particle. Then these properties must exist in the second particle, both of them. If, again, you have this locality.
Let me just comment further. You know, when I see this thing, if in fact you measure the position of one particle, then you would know the position of the other particle if they're
Right.
entangled. But if at the same time you measure the momentum of the second particle, you'd know the momentum of the first particle.
You can't simultaneously do the two. That's the uncertainty principle. You can't do position and momentum together.
If you measure the momentum of the second particle, then you don't know its position.
Can I ask
Or
you?
you've destroyed its position
Yeah.
when you measure its momentum.
Yeah. That's why you want to do everything on the first particle, because you're not disturbing the second particle.
Can I ask you just one thing? When you measure them on one particle, the first particle, you set up your measurement in such a way that you get a certain position of the, let's say, the momentum. That would be meaning that the entangled particle has also a known position at the same time.
Okay.
Now, you change the measurement condition, make it to the opposite. The funny part is that immediately then the entangled particle was changing also, which you know to what. So how did they communicate?
Well, of course, that's the
Now that's the problem.
non-locality
Yes.
that apparently is.
We're going to get to non-locality and contextuality. That's the solution to that problem.
Yes.
Can I ask a question here? Isn't the EPR paper where they introduce the idea of hidden variables?
Yes.
And how does that work into this?
Well, the fact that you can simultaneously measure the position and the momentum. Quantum mechanics says you can't.
Yeah.
The argument of EPR is that here's a way of doing it with these two entangled particles, just by choosing what you want to measure in the first part. The fact that you You may not be able to measure both at the same time on the first particle, but the fact that you can choose to measure one or the other, and you'll get a definite result for the second particle. And there's no way for the first particle to communicate with the second particle. Means the second particle must have that information somehow or other encoded in it, and that's where the hidden variables come in.
But that's not accurate. That's not the way quantum mechanics works. So that's what Einstein unfortunately got wrong.
Yeah.
I still don't understand. You can measure either the position or the momentum
Yeah.
of the first particle.
Yeah.
So what?
Well, that tells you what those quantities are for the second particle.
Okay,
But
so
you haven't disturbed, you haven't touched the second particle. So presumably those quantities have an existence in the second particle.
That was the assumption that Einstein made that was wrong.
no, but I'm trying to understand his wrong argument. You know, I don't care that it's wrong. I just want to understand how he was arguing it.
Well, his argument was, if I can measure one and know without disturbing the second one, knowing what that one is true,
I can
two places, I can either do position or I can do momentum, and I cannot disturb the second particle because I only measure one, and therefore, if I can choose one or the other, both of those quantities must exist before they're measured. That was the argument. That's the argument that's wrong. It's not true. Those properties do not exist a priori until they're measured.
You're not saying that you have measured both. What you're saying is that you can choose, you have a choice to measure either one or the other.
Yep.
But you're not disturbing the second particle. So the second particle is going to have a definite momentum if you measure the momentum of the first particle. It's going to have a definite position if you choose to measure the position of the first particle. But because the second particle is far away, these two properties must exist in the second particle. Because how do they come about if they don't already exist in that particle? How can a particle? Let me see how I can say it. The fact that you can choose to measure either one and get a precise result without disturbing the particle means that both properties must be there in that particle.
Yeah, the idea in classical physics was that every entity, every system had a collection of properties, and those were known from the initial conditions and continued to exist forever. That's not the case in quantum mechanics. You don't know the initial conditions, first of all, and second of all, you don't know the properties until after they're measured.
Well, I have something to ask. So what you have is two particles, for example, which are mirror twins of each other, in effect. They don't communicate, but they both start out at the Big Bang or whenever with the same momentum, and therefore always end up in the same or predictable positions. If you measure one, you can predict the where the other, or you know for certain where the other is. What if while they're traveling, one of the particles?
No. You're talking classical. They're not traveling any place. You don't know what they're doing, where they are. You don't have any of that information. This is quantum mechanics, not classical.
I think what you're trying to say, Bob, is that until you attempt to measure, or until you actually measure one of those particles, its momentum and its position are undefined, except in a probabilistic way. Is that correct?
Yes, they just, you do not know. They could be any place. They could be, because when you measure it, you might find it to be in Alpha Centauri, not in the laboratory.
But when you measure it, can you ever find it to be in exactly the same place that it started?
Yeah.
So, all right, so there's, so.
So you don't know where it's going and what
Laboratory stayed stationary.
you have no information. Quantum mechanics cannot tell you what happened between the initial conditions and the measurement.
Okay, but if I measure the position of one of those particles, there's some dynamic equation or something that says, I know what the position of the other one is. There has to be some relationship between the two of them.
You have to conserve momentum
Right.
and so on.
So there's some, there's got to be some equations of motion or whatever it is that describes where.
Yeah, no. The equations of motion are only on average. And you have to do an infinite set of measurements in order to get the average. So you do not know any individual particle. You only know the average over an infinite number of measurements. You have to do it over and over and over and over again. You have to measure it repeatedly. Then you will get a trajectory, and the trajectory will be the classical trajectory. But that's only an average over an infinite number of repeated measurements.
Okay.
I'm going to just ask one more question. If the EPR article were correct, if it were correct, it would have proved that there were hidden variables.
Yeah. I guess what, if you use the words essentially that they use, they said a property of the system is a property that can be measured without disturbing the system. And it must have a counterpart in the mathematical theory. Now you have two properties that can be measured without disturbing the system. You have the position and you have the momentum, because you're not disturbing the system because you're doing it on the other particle. So the argument is that these two properties must have a mathematical counterpart in the theory. And this mathematical counterpart is a hidden variable. Okay, but again, I think the chief property that Einstein was concerned with was locality.
And we'll get to locality and how it goes away in contextuality when we get there. So can we move on to reality a little bit here?
Reality is boring.
So Rene Descartes, who's known as the father of modern philosophy, began his question with, how do we know there's any reality outside of our own minds? we each know we have experiences and we can be sure of these experiences. Therefore, we can never be sure that we exist. How do we know that we have internal experiences that correspond to objects outside our minds? The answers that philosophers have come to is observations. The study of the patterns of observations is science. And so philosophers have basically said that the best theories of science define reality. When most people think of experts, think of subatomic reality. I think I yeah. Oh, I'm sorry, yeah. When most people, including experts, think of subatomic reality, they imagine of particles, and particles behave like little billiard balls rebounding off one another. This notion of particles is a holdover from the ancient Greek atomists and reached its pinnacle in the theory of Isaac Newton. Unfortunately, the core of quantum field theory, nothing behaves like billiard balls at all. Whenever you think of particles, you're wrong. They're not there. The classical concept of particles says something exists in a certain location, but the particles of quantum field theory do not have well-defined locations. A particle inside your body is not inside your body. An observer attempting to measure its position has a small but non-zero probability of detecting it in some remote place of the universe, could be in a different galaxy. This contradiction was evident in the earliest formulations of quantum mechanics, but became worse when physicists added special relativity theory. Relativistic quantum particles are, and I should really use scare quotes around particles because they're not particles. They're extremely slippery. They can't be found in any specific region of the universe at all. So let's suppose you had a particle localized in your kitchen. Your friend looking at your house from a passing car might see the particles spread out over the entire universe. Remember, special relativity says everything depends upon the observer. So what's localized for you is delocalized for your friend. Not only does location of the particle depend on your and all other observers' point of view, so does the fact that the particle has location. In this case, it doesn't make sense to assume localized, quote, particles, unquote, as the basic entities like billiard balls. So that's, you can't even necessarily localize them except for a particular observer. Are we good on this?
Well, I'm still worried about tracks in a cloud chamber.
Yeah, but that's all you have in a cloud chamber is individual events. And then you track them together and you use them to make up a trajectory. But you don't know in particular a priori that they're taking a trajectory. And the quantum mechanics of it is slippery. It's less so in quantum mechanics, but more so in quantum field theory.
Bob, I just want, one of the things you said, a particle can't exist in relativity. You could have a particle at some point in space-time and every observer would agree that it's at that same point. Is that not true?
I'm sorry, could you repeat it again, please? I want to make sure I hear it correctly.
Particles can exist in relativity, and you
Well,
could
they
have,
can exist in relativity. They can't exist in quantum field theory, which is the relativistic version of quantum mechanics.
okay, I thought you were giving an example that different observers might think that the particle in your body were at a different location if they're forgetting quantum mechanics because they were traveling at different speeds.
No. It's the fact that it's quantum field theory that is consistent with special relativity that means the result is not localizable except to a particular observer.
So I have a question here. When you have a measuring device, of course, it's a classical thing, but it has a definite location. And so if I measure a quantum particle, the locality of it, does that not tie it down to where that measurement device is?
That's a very slippery question, and it's a very complicated answer, which I'm going to hopefully get through as
Okay.
we go through the remainder of this.
Okay.
Even if you try, okay, so give up trying to pinpoint the articles, where the particles are, where they are, and simply count them. You're still in trouble. If you know the number of particles in your house, you go around the house, you find 3 particles in the dining room, 5 under the bed, 8 in the kitchen room, and so on. Now you add them up. Surprise, surprise. You find the answer in quantum field theory says that that's not the answer. The numbers that you measured and you added up together are not the number. The only way quantum field theory says you can do it is as a property of the house as a whole. So you'd have to measure the whole house simultaneously rather than room by room. And why can't you do that? Simultaneity, what doesn't exist in, when does simultaneity does not exist? In special relativity?
No,
Are we
yes.
there? We know the thing that Einstein gave us with special relativity is simultaneity doesn't exist.
It's different for different observers, yeah. Go in a different.
So you can't do a whole house simultaneously because you'd have to have a magic observer who could do it, and it can't be done. So an extreme case of particles being pinpointable, is in the vacuum. The vacuum has paradoxical properties in the quantum field theory. You can have an overall vacuum, by definition, a 0 particle state, while at the same time you observe something very different from a vacuum in a finite region. In other words, your house can be totally empty, though you can find particles all over the place. If the fire department asked you whether anyone was still inside a burning house and you said no, the firefighters would question your sanity when they discovered people huddled in every room. So this is a very strange property of quantum field theory. Another striking feature of the vacuum in quantum field theory is the Unruh effect. And we've talked about that when we talked about the Hawking radiation, Unruh effect is very similar. If an astronaut was at rest, they may, and they're in a vacuum, then the astronaut will feel they're not having anything there. But another astronaut is in an accelerating spaceship moving right next to you will feel immersed in a thermal bath of innumerable particles. This is the special relativity version of what Hawking radiation did at the event horizon of a black hole. So if a vacuum is filled with particles, sounds absurd, that's because the classical notion of a particle misleads us. What the theory is, what quantum field theory is describing is something else. The number of particles is observer dependent. And it seems to be incoherent to assume that particles are basic if if the number of particles is observer dependent. So we can't really think about particles as being fundamental. Finally, quantum field theory says particles can lose their individuality. In the puzzling phenomenon of quantum entanglement, which we've been talking about, particles can be assimilated into a larger system and give up the properties that distinguish them from one another. The presumptive particles share not only innate features such as mass and charge, but also spatial and temporal properties over ranges of position where they might be found. This is the EPR argument. When particles are entangled, an observer has no way of telling one from the other. So if at this point, I don't think we will believe that particles ever exist. Entangled system behaves as an indivisible whole. And the notion of a part, let alone of a particle, loses its meaning in quantum field theory. So the name quantum field theory connotes a theory that deals with quantum versions of classical fields, such as electric and magnetic fields. So what's the quantum version? The term field, what we think of when we think of classically, such as magnetic fields, will cause iron filings to align themselves around a bar magnet, or electric fields cause your hair to stand up on end. But a quantum field theory is a very, very different object from a classical one. And most theoretical physicists can barely visualize it themselves. Classically, again, a field assigns a physical quantity, such as temperature or electric field strength, at each point in space-time. A quantum field instead assigns an abstract mathematical entity known as an operator and represents the types of measurements you could conduct. So rather than the result you would obtain. So it tells you, the field defines what are the possible measurements you could do, and those are known as operators. And So the mathematical constructions in quantum field theory don't represent physical values. They cannot be assigned to points in space-time. They're only, you know, they could be any place. They're smeared out regions. Historically, physicists developed quantum field theory by quantizing classical field theory. This is what people talk about, putting hats on all of the objects that there are in the field. That is, you replace the possible results with operators. You replace the physical values with mathematical operations such as differentiation or taking the square root. It's not taking the square root of something, it's just taking the square root. It's an operator. You could take an operator on anything. And some operators correspond to some specific physical processes such as emission and absorption of light. So operators place a layer of abstraction between quantum field theory and reality, because you don't know anything about the results of a measurement. You only know what the measurements could be at every place in space-time. A classical field is like a weather map, shows temperature in various cities. The quantum version is like a weather map, but it doesn't show you 40 degrees. But remembering that the temperature is an average over energy, the operator would be the sum over all the masses of the atoms of the various gases that you're around, with the Laplacian plus whatever the potential might be, usually gravitational or some other fields. So the quantum field theory gives you a location at every place in space-time that has this operator. If you want to actually get a temperature value, you need to add another step. And that step is the state vector, usually defined by some psi of x and t, which represents the configuration of the system in question. I've said an awful lot here that is quite complex. Did anybody follow what I was talking about?
Well, I worry about the temperature. That's just a statistical quantity that you have to extract from, say, the entropy of a system. But your other parts are, I'm fairly comfortable with them.
Is an operator a mathematical version of an observer?
No, it is a potential measurement. And a measurement doesn't have to occur by an observer. When two particles interact with each other, that's a measurement. So, and what happens is their state vector, the psi function, becomes entangled. The space that it was initially far removed, when they got close to each other, they became the same entity, or at least partially the same entity. They lost their identity as two particles and became a partial one entity.
An operator can take on many forms depending on the mathematical theory. The simplest example would be take the velocity of a particle and multiply it by its mass. You can think of that as an operator, and that gives you the momentum of the particle in classical physics. Or take the gravitational potential, take the derivative of that, that gives you the force. That would be another example of an operator. But an operator can be something that's extremely simple, like multiplying the velocity by mass to get a momentum. Or depending on the theory, it could be more abstract. But it's some mathematical manipulation that you do.
Yeah, the momentum is h bar over I partial gradient. So they're all mathematical functions or operations, things that could be put on something. You don't know what the result of an actual measurement is without knowing what the state vector is of the system. So the field, the quantum field doesn't tell you what the results are. It only tells you the positions of various kinds of measurements that could be taken.
Bob,
Bob,
go ahead.
I'm way back with that vacuum thing. I'm having trouble. I'm sure this is a relativistic thing, but it's hard for me to visualize. A vacuum is a vacuum. So if it's a vacuum, how can you be observing particles in it?
Yeah, some people can, some won't. Depends upon their system, their relative motion to those particles. And for some observers, that there won't be any particles. For some observers, there will be some.
So for some observers, the vacuum doesn't exist.
I don't know what that means. What do you mean it doesn't exist?
Well, if I observe particles in a certain space, then it's not a vacuum.
To that observer. But other observers see no particles. So they see a vacuum.
Pardon me?
I said other remember, there's an infinite number of possible observers, all moving at different velocities. And some other infinite possibility of those under acceleration. And everyone will see different sets of particles. Some none, some there.
Okay.
So the vacuum isn't well defined.
Bob, are these particles or virtual particles?
No, they're particles.
If you can think of the vacuum as the lowest energy state of the system. And non-accelerated observers are going to see only virtual particles, don't see any real particles in the vacuum. But accelerated observers, and as counterintuitive as it sounds, will see real particles. An accelerated observer is equivalent to an observer undergoing the same gravitational acceleration, say, near a black hole. Now, a black hole emits Hawking radiation. So the observer that's near a black hole and is experiencing gravitational acceleration is going to see Hawking radiation. An observer in far away from a black hole, but undergoing an acceleration, should be completely equivalent to an observer that's near a black hole. And therefore, he should see radiation as well. In fact, he sees Hawking radiation.
And that's what's called Unruh radiation.
Yeah. It's very, as I say, it's very counterintuitive, but that's it.
Well, wait a second. I mean, seem to be saying two different things. two different observers in two different positions or locations will observe different things. For example, one will observe no particles in the vacuum, and others will observe a lot of particles in the vacuum. But now you're saying, if you have two different observers in relation to the event horizon of a black hole, they'll both observe the same thing, even though they're not in the same location.
That's the equivalence principle from general relativity. Anytime you have a gravitational field, it's the equivalent to an accelerated inertial frame. Or in general relativity, it's an inertial frame. So that's just the equivalence principle. That's true. If you're far away from any gravitational field, but you're accelerating, then that's an equivalent to a different gravitational field. That's the equivalence principle. And therefore, you have to see the same result as you would at the event horizon of a black hole.
Yeah, in this particular case, the two observers we're talking about are equivalent.
Okay.
That's why they see the same thing.
Oh, okay. So you're defining them as equivalent.
Yeah,
So that's.
we're specializing to the case where the two are equivalent, and therefore must see the same.
Okay.
Yeah.
Well, another thing I wanted to do then is go back to Descartes' original question of what is reality, which you posed here. So if reality, I think you said, according to science, it's dependent on observation. But if you have two different observers, and we're not talking about their equivalent, we're talking about the vacuum hypothetical that you just gave. If you have two different observers, one observing particles, another not observing particles in that same vacuum, then what's reality?
Well, the reality is that it's observer dependent.
Okay, so there is no such thing as reality that everybody agrees on.
That's what we've been trying to say that's what Einstein kept trying to say, was that there is a reality independent of people. And what quantum mechanics says, the universe has properties, but those properties depend on observers. And observers only mean particles interacting with each other. It doesn't mean, when we talk about observers, we're not talking about human beings. We're not talking about mice. We're not talking about bacteria. We're not talking about viruses. We're talking about two particles interacting with each other. That's what an observer is.
Yeah, now, if we go back to Einstein and reality, he didn't say that there's this reality that looks the same to all people. He says there's this reality, this underlying reality, but it depends, what it looks like depends on your state of motion. Okay.
Yeah.
Bob, I just had a comment on the previous slide before you go forward. Can you go back to it? In that equation, that Vx, that should be xi, x sub I, I mean, the summation is over the.
Yeah, it should be. Or you could consider it to be the configuration space.
But if it's included in the summation, it would have to be an x sub I.
Yeah, that would have to be x sub I, correct. I apologize.
I have a question about so if you entangle two particles, then you have to treat them as one. So if we entangle two electrons, they have a charge of -1 each. Does this mean we now have a particle with a charge of -2? How does that work with all those conserved quantities? And we know that, in some sense of the word, that we know that this entangled particle has.
Actually, there's no such thing as conservation of charge in quantum field theory.
Or
there is quantity, you know, energy is conserved, but charge is not conserved. We measure it as conserved, but it's not conserved in quantum field theory.
Well, you're saying we don't know a symmetry that conserves charge.
Right.
What about the what about U1 gauge theory?
Yeah, that's what I was thinking about, you know, all of those numbers that are so
Yeah.
particular to
I would think that would
particle physics.
conserve electric charge.
I would have to look it up, but I don't believe there's a symmetry that allows conservation of charge, but I could be wrong.
Yeah, there's corresponding symmetries that conserve things like weak, whatever that's called.
I know they're not quantized, that's for sure.
Weak, anyway. So
Anyway, if we could move on, I've only got another 45 minutes and I got quite a bit of work I'd like to do. So at some level, all of this peculiarity of quantum field theories is really not surprising. Quantum mechanics, the theory on which quantum field theory is based, does not traffic in determinate values either, only in probabilities. Ontologically, the situation seems weirder in quantum field theory because the supposedly fundamental entities, the quantum fields, do not specify any probabilities, but you have to combine them with a state vector. But ultimately, quantum mechanics, once we get to contextuality, a lot of this will get clearer. So in his first paragraph of his infamous cat paper, Schrödinger pointed out the relation of reality in our model of it. The model is an abstract construction that focuses on the important aspects and in doing so ignores peculiarities of the system. It simplifies the reality. This approximation is arbitrarily set by human beings. As he states, without arbitrariness, there is no model. This simplification is done to achieve an exact way to calculate, and herein lies the difficulty with a quantum mechanical system. The model of quantum field theory contains less information for the final state system than its initial conditions that would normally tell you everything in a classical system. So back to our shapes. We're coming back to our shapes, finally. Cakes don't count as quantum systems, of course, but the entanglement between the quantum systems arises naturally, for example, in the aftermath of particle collisions. Quote, again, scare quotes around particles and scare quotes around collisions, because there aren't any particles and there aren't any collisions. In practice, unentangled independent states are rare exceptions. For whenever systems interact, the interaction creates correlations between them. And so that's the idea. What a quote collision is simply the two particles get close to each other and they become partially a complete system, not individual systems. And for our example, we could write a wave function for the circle, a wave function for the square, and describe its system one in terms of phi circle and phi square, and system two psi square and psi circle. And then if you work out the examples of the wave state, the wave functions, for independent ones, you have the two systems multiplied together. So you get 4 terms. You get psi circle, psi square, I'm sorry, phi, phi circle, psi square, phi circle, psi circle, phi square, psi square, etc. The entangled is only the circle, circle, square, square. And it's pretty clear when you take a look at the fact that there are the parentheses there that the systems are independent. The two sides have all of the properties of the system, and the total system is the sum of all of the different pieces. The entangled system is a composite system. You can't take partial information. It's either going to be circle, circle, or it's going to be square, square. You don't know which, but it's going to be one of those two. So previously we imagined that our secons, our ceons, would be square and circle, and we could exhibit, for example, another case where we also had a second property, red and blue. And if we were speaking about classical systems like cakes, this would add a property that would imply our ceons would be in any of 4 possible states: a red square, a red circle, a blue square, or a blue circle. So for quantum cakes or QANs, the situation is profoundly different. The fact that a QAN can exhibit in a different situation, different shapes or different colors doesn't necessarily mean that it possesses both a shape and a color simultaneously. This is what we've been talking about in the EPR experiment. So, in fact, it is, if you try to measure 2 things simultaneously, you can't do it. That's inconsistent with experimental fact. So we're going to assume that our quantum operators for shape and color do not commute. This is the consequence. And we can measure the shape of our QANs, but in doing so, we lose all the information about the color. And if we measure the color, we lose all the information about its shape. So what we cannot do, according to quantum theory, is measure both its shape and its color simultaneously. So no one view of physical reality captures all of its aspects, color and shape. One may take into account many different mutually exclusive views and get partial insight. So the process of measurement proceeds until some property is identified and the measurement is then complete. Until then, all of the values of the properties are not known. Only once a property is discovered by a measurement process is it completed and no other properties are available. As a consequence, quantum theory forces us to be circumspect in assigning physical reality to individual properties. To avoid contradictions, we have to admit that a property is not measured, need not exist. That's a complicated statement. Hopefully people understand it. If you haven't if it hasn't been measured, it hasn't interacted with something else, it need not exist. And measurement is an active process that alters the system being measured. So the results, a measurement is a process that will go in contextuality in a hopefully fairly shortly to show how it actually works.
Bob, is your first statement consistent with Bohmian mechanics?
No, Bohmian is a way of dealing with things as beables, not as quantum. So I'm avoiding Bohmian right now.
Okay.
Well, if I suppose I decide to measure shape, so I make a gazillion measurements of shape and it comes out to be a circle. Then can I now do a gazillion measurements of color and it comes out to be a blue? And I conclude now that it is a circle and that there are circles and blue, there are blue circles. Can I make that conclusion?
No. No. The blue could be a circle or a square, and a red could be a circle or a square. No matter how many times you measure a circle, you don't know whether it's a circle or a square. I mean, it's red or blue.
Right.
When you do the second measurement,
Right.
you mess up the information that you obtained from the first measurement.
You lose all that. Okay, thank you.
Okay, so
Could I want to ask something. You lose all that because when you make your second measurement, a function of time has happened. In other words, you can't do it simultaneously. Can you do it?
yeah, you can't do them simultaneously, and you don't know what the properties are. When you measure the circle or square, you know it's one of two possibilities, and even if you get 1,000,000 of them at circle, you don't know the color.
Right.
And if you do 1,000,000 measurements of color, you don't know the square or circle.
You can't do both.
You can't
put them
then
together.
measure something later.
You can measure it later, but then you destroy the information that you had obtained in the earlier measurements.
Is it destroyed or it no longer exists because it's later in time?
Well,
In other words, the earlier measurement
We
is.
can get to contextuality, you'll get to see how properties become. They become in a process of measurement. So I'd like to, I don't know how much further I got to go here. Let me try to finish up fairly quickly and get to contextuality, because that's important. So we've done illustrations of quantum theory's strangeness. The EPR pair consists of two QAns, and that can be measured either its shape or its color, but not both. And you can assume access to all pairs are identical, and we choose to do it over and over and over again. The interesting effect with EPR considered paradoxical arises with the measurement both members of the pair. And we remember, whenever we know the shape of one, we know the shape of the other, and if we know the color of one, we know the color of the other. And that is the strangeness of entanglement. And the fact that these can happen over great distances implies that there is what Einstein called spooky action at a different distance. And it seems to require the transmission of information about a measurement was performed at a rate faster than the speed of light. But does it? Until you know the result you obtained, you don't know what to expect. So you can gain useful information only when I learn the result that you've measured, not the moment you measure it. Any measurement, any message revealing the result would have to transmit some concrete physical way, a slower, presumably, than the speed of light. And the paradox actually dissolves a little further. If you consider again the state of the second system, given that the first has been measured to be red, we can choose to measure the second QAn's color, we will surely get red. But we discussed earlier, if we choose to measure a QAn shape when it's in the red state, that will have an equal probability of finding a square or a circle. So far from producing a paradox, you're logically required to have the results that quantum mechanics give you. So if you take a look, you can measure color. Colors the same will be 100%. You can measure shape. The shape will be the same, 100%. But the color, if you measure it when you measure shape, the random will be 50%. And if you measure color and the other one measures shape, the results will be 50%. So they're all internally consistent probabilistically. And that's the only results that quantum mechanics gives. So I'd like to move on to contextuality. We still have almost a half an hour, so hopefully I can get through this because it's important. We've run the contextuality game once before, but I don't know if many people remember it. The idea is that you want to discover who of a set of scientists were by asking a series of questions. You can ask questions about gender. You can ask questions about title. You can ask questions about what they're known for, and you can find out what prizes those scientists got. So Hedy Lamarr was a female. She was an actress and engineer. She's known for spread spectrum techniques, and she got the National Inventors Hall of Fame prize. Albert Einstein was a male, a physicist. He's known for entanglement and general relativity, and he got the Nobel Prize. Katherine Johnson was a female. She's a mathematician. She computed the trajectories for Project Mercury, the Apollo 11, and the Space Shuttle, and the Congressional Gold Medal. Niels Bohr was a male, a physicist known for quantum mechanics, and he got the Nobel Prize. And Marie Sklodowska-Curie was a female, a physicist and a chemist known for discovering radium, polonium, and radioactivity, and she received 2 Nobel Prizes. Kip Thorne, a male physicist, general relativity and LIGO, and he got the Nobel Prize as well. So if we were going to run this program, we would have everybody go out of the room. I mean, the person who's going to be the chooser is going to get out of the room. And we tell everybody the rules are the following. Everybody chooses their own person, their own scientist that they want randomly. I mean, however whatever reason they want for. And then the questioner, when he comes back in, will only ask yes, no questions. And each questionee has to answer accurately. Once the answer is asked, for example, is the scientist male? If the answer is yes, then everyone who chose a female scientist must change their answer to a male scientist. On the other hand, if the answer was no, then everyone who had a male scientist had to change their answer to a female scientist out of our collection of 6. And the questionee keeps asking questions until the entire group of questionees have only one resulting same scientist, and that's when the game stops. Now, everyone, when they choose a new scientist, has to be accurate to all previous questions. So if they were a female and a physicist, they couldn't change it to a female and a mathematician if everybody had said they were male and physicist. So you have to be consistent in all of the questions going forward with all of the questions asked previously. So here's an example. You have a first question, gender. Is it a male? You ask questionee number 4. The questioner doesn't know that the questionee chose Hedy Lamarr, and the answer is false. So everybody who had a male out of the 15 questions, you have all of the male scientists have to be thrown away, and everybody has to choose different female ones. Now, the second query he asks is it a mathematician? And the question he asks is number 7. And the questioner doesn't know that that same person also chose Hedy Lamarr, but the answer is false. So now the third career, the third category is career, and the query number 3 is, was it a physicist? And the questionee number 6 is number 6. The questionnaire doesn't know that the questionee chose Marie Sklodowsky-Curie, but the answer is true. And therefore, going back to our list of people here, the only females who got the Nobel Prize were Marie Sklodowsky-Curie, and therefore, with the answer true, Marie Curie is the unique scientist. So the contextuality game is to keep choosing until you find a unique scientist by asking a series of yes/no questions. So here's another example. Query number 1. Was the scientist known about entanglement? Questionee number 3 doesn't know that he chose Albert Einstein, but it says true. And since in our original one, the only one who was known for entanglement is Albert Einstein, the unique answer is Albert Einstein. So the way in which contextuality works is all different possibilities are randomly chosen. And then you select from them by various properties in a series of yes/no questions, and eventually you get to a unique scientist. So quantum contextuality was first demonstrated to be a feature of quantum mechanics by the Bell-Cohen-Specker theorem. And Bell determined it well before Cohen and Specker, and it used to be called the Cohen-Specker theorem. Now it's called the Bell-Cohen-Specker theorem. Bell did an awful lot of good stuff. Quantum contextuality is a feature of quantum theory whereby measurements of quantum observables cannot simply be thought of as revealing pre-existing values. Any attempts to do so leads to values that are dependent upon which other measurements are being performed, the measurement context. The study of contextuality has developed into a major topic in quantum foundations recently, and crystallizes the non-classical counterintuitive aspects of quantum theory. So you have to think of a measurement, that is an interaction between any two quantum systems, as a series of yes/no questions going on between the two systems as they interact. And when they come out, they have a certain set of properties as a result of the interactions. Non-locality, one of the things we've been talking about, the thing that drove Einstein crazy, in the sense of Bell's theorem, can be viewed as a special case of the more general phenomenon of contextuality, in which measurement contexts contain measurements that are distributed over space-like separated regions. So the fact that you don't know which location is possible can be distributed over very large space-like separated regions. If you remember from your special theory of relativity, time-like are causal, space-like are non-causal. So non-locality means that your measurements can be distributed, your fields can be distributed over space-like separated regions. And whenever an interaction occurs between any two systems, a series of yes/no questions has to be answered in order to get the results out of the interaction. Okay, before we move on to next week, contextuality. Do people understand how it works?
Yes. The questions, the different categories you had, they carry different amounts of information. Like male, female is one bit, but the the prize that they won, there were 4 different possible states, so there were 2 bits of information there, and I think it was 3 bits in the other one. Does that matter?
Would somebody repeat the question for me, because I couldn't understand it?
I think I'm going to let you try again, just with the microphone closer.
Okay. So what I was concerned about was the different categories of information that you had for each scientist were like male, female was one of them. And then the field that they worked on was another one. And there's 1, 2, 3, 4, 5, 6 different scientists. Okay, so we've got gender is really distinguished by 1 bit of information because there's only 2 states. Whereas what they're known for, there's 6 different things that they're known for. So there's actually 3 bits of information there. And so, and as we saw, by guessing correctly on what you're known for, you can go directly to one scientist. You can force it to one scientist, right?
Right.
Because it carries much more information, that particular question. Does the information content of these categories affect the idea of contextuality is what I'm trying to get at.
No, if I ran this in a computer program 10,000 times, and the answers always turn out to be uniformly distributed among the 6 scientists. So the fact that there is uneven amounts of information within the different categories doesn't mean that the results will be uniformly distributed.
Okay.
I had 2 pictures, one that showed the histogram of the various scientists, and they turned out all to be even. And then another one that showed the number of questions that took between 1 and 10 in various probabilities. Those were uneven. The number of questions that you needed to receive to get a scientist were uneven, but the results of what the scientists were all uniformly distributed.
Okay.
Bob, I thought I understood the game, but now on reflection, I'm not sure I do. Could you just repeat the rules?
Okay. So each questionee, and in the case of what I did in the program, I chose 15 people randomly choosing the scientists. Then the questioner who was not there while people chose them asks only yes/no questions. So, for example, he could say, "Is it a female?" And the answer would he has to choose one of the 15 people randomly or however he wants to, but he can't just keep asking the same person over and over again. He has to ask different people.
Okay, I think I understand now. For 1 minute there, I was wondering how it differed from 20 questions, but obviously there's a big difference.
Yeah, in 20 questions, people all ask a priori to pick a single person.
Right.
In this game, everybody chooses whoever they want. But after each questionee answers accurately, everyone who didn't answer, it didn't have a characteristic of the scientist they had chosen, had that characteristic, has to throw out that person and add another person who did have that question. And in fact, all previous ones as well.
Yeah, I understand.
Okay. And eventually everybody gets the same scientist, and that's when the game stops.
Process of elimination.
Yeah, but it's unlike 20 questions, each different question.
Each person chooses randomly or whatever reason they want to, but they have to agree that whenever somebody asks a question, if their person doesn't satisfy that question, they have to throw out that person and find a new person who has the same characteristic that was just answered yes or no.
So each person's choice of a scientist depends on what went on before. It has to be consistent with the answer that have been previously elicited.
Yeah, and it's changing. Each person's thing is changing all the time as each question gets asked.
Right. So each questionee has to have a scientist in mind who has characteristics that are accurate to all previous questions. That's the way in which they eventually get to a single person.
Yeah, before we go, we have to decide about the near future. Next week is Christmas Eve. The week after that is New Year's Eve. Are we going to meet?
What's the consensus?
Well, personally speaking, I won't be here the next 2 weeks. Everybody else will be.
I won't be here either.
I will be here next week.
Yeah.
There's a lot of people missing already.
Yeah, maybe we ought to skip over the next couple of weeks, because I think a lot of people will be pretty busy or be out of town.
Yeah, I think those 2 weeks would probably be bad weeks in general.
Actually, you can have a small group today. More regular.
Okay, I'm willing to skip for the next 2 weeks, and then I'll come back with open systems, closed systems, coherence and decoherence, and the result, which is Ein selection and pointer states. And when all of that is put together with probability and logic, you wind up that quantum mechanics is actually classical mechanics when you're 6 feet tall and have 10 to the 24th atoms, all entangled with a quantum mechanical system.
Well, we'll gird our loins.
We don't show up, it's because that's not true. We participate into the four corners of the galaxy.
So it's January 7th, is our next one, right?
Yeah.
But contextuality, the way in which measurement process occurs, it actually creates the process of the momentum, the position, whatever it is that you're measuring, through a series of yes/no questions based on the results of the operators in quantum field theory.
Is that your time?
This is, no, this, if anybody wants to see this, this is a plate, Copenhagen.
And I'll send that out again in this next email.
Okay.
Mention.
It's a
I'm going to
plate.
stop the recording now.